In this problem, we want to find all functions f such that it's a function from the integers to the integers, such that for all integers x and y, f of x minus f of y equals to f of x minus y. Now, this problem looks intimidating because of the nested functions and the mix of variables. The key to solving functional equations like this is to substitute specific values to improve general properties of the function, one step at a time. So, how do we solve this problem? First, let's see what happens if two different inputs, y1 and y2, give the same output. We can assume that fy1 equals to fy2. That's going to be the first step to our breakthrough. Assume f of y1 equals to f of y2. Now, if we plug these into the original equation for y1, it would be f of x minus f of y1 equals to f of x minus y1. And for y2, f of x minus f of y2 will equal to f of x minus y2. And then, since f of y1 equals to f of y2, the left-hand sides of these two equations are identical, and that will mean the right-hand sides must be equal too. So in other words, f of x minus y1 equals to f of x minus y2. Canceling out or subtracting f of x from both sides will give us negative y1 equals to negative y2, which will mean that canceling out the negative signs will give us y1 equals to y2. This proves that the function f is injective, or in other words, 1-to-1. And this is the breakthrough for the first step. It tells us that different inputs must lead to different outputs. Now, let's look at the right-hand side of the equation. f of x minus y. Pick any integer you want, let's call it k. Can we make the function's output equal to k? Let's fix x to be any integer, for example, say x equals to 0. The term f of 0 is just some fixed integer constant, which we can call as c. So, the equation's right side becomes c minus y. Now the question is, can we make c minus y equals to k? Well, yes. We can just choose y equals to c minus k. Since c and k are integers, y will also be an integer. So, since c and k are integers, we'll have y will also belong to integers. Now, this will mean that the output of the function f can be any integer k. Therefore, the function f is surjective, or onto. Combining steps 1 and 2, we know that f is a bijection. Well, what's a bijection? Well, basically, in simple terms, this is a good thing for us, as it means f is a perfect permutation of the integers. Now, since the function is surjective, there must be some integer input, which we can call as lowercase c, that produces the output 0. So we can say that f of c equals to 0. This is our secret key. Let's substitute y equals to c into the original equation. So plugging in y equals to c would give us f of x minus f of c would equal to f of x minus c. And then, since fc equals to 0, we'll be having f of x minus 0 equals to f of x minus c. Or the 0 part just cancels out. So f of x equals to f of x minus c. This simplifies to a new rule for our function, which is we'll be having f of x would equal to f of x plus c. We got this just by moving the minus c to the left side. We have f of x equals to f of x plus c. Now we're getting close to the ending of the question. We can use our secret key f of c equals to 0 again, but this time by substituting x equals to c into the original equation. So we'll have f of c minus f of y equals to f of 0 minus y. But wait, we have a relationship between c and f0. Let's use our new rule, f of x equals to f of x plus c, with x equals to c. So we'll have f of c equals to f of c plus c. Then plugging it in will give us f of 0 equals to 0 plus c. So f of 0 equals to c. Now we can substitute this back into the equation we just found. So we'll have f of c minus f of y equals to c minus y. This is the final piece of the puzzle. We can apply the function f to both sides. So we'll have f of c minus f of y. Be careful with the parentheses here. Equals to f of c minus y. So, using our rule, f of x equals to f of x plus c, the left side becomes f of c minus f of y plus c. So, then simplify, we'll have c minus y plus c equals to f of c minus y. Then f of c minus y will equal to 2c minus y. Let's make a substitution to clean this up. Let w equal to c minus y. Then, as y ranges over all integers, w also ranges over all integers. We can express y as y equal to c minus w. F of w will equal to 2c minus c minus w equals to c plus w. This reveals the form of our function. It must be in the form of f of x equals to x plus c. So now we've deduced that if a solution exists, it must be of the form f of x equals to x plus c. Now, we must plug it back to the original equation to see for which values of c it actually works. Remember that the original equation was f of x minus f of y equals to f of x minus y. The left-hand side was equal to f of x minus f of y. Then this will equal to f of x minus y plus c. And then this will equal to, well, x minus y minus c, which just equals to x minus y minus c plus c. The c's cancel out, so this will equal to x minus y. Now the right-hand side. The right-hand side will equal to f of x minus y equals to f of x plus c minus y. And then this will equal to x plus c in parentheses plus c minus y. So it equal to x plus 2c minus y. So the only possible choice after comparing these two expressions will be c equals to 0. So the conclusion is, since c equals to 0, the only possible function is f of x equals to x plus 0, which just equals to x. So the one and only function that satisfies the condition is the identity function f of x equals to x. And that is the answer to this problem.